So, link local addresses can serve as a way to connect devices on the same local network without needing global addresses. It's pretty rare that you would just say, I want to talk on my local network with IPv6, but if you're in a testbed environment like I am at home a lot, and I want to use Server 2008 and Vista to communicate together, I just set up IPv6 and I'm testing, I want to use an analyzer, I just use the link local addresses. When communicating with the link local address, I must specify the outgoing interface because every interface is connected to FE80. So this is going to take some thought. IPv6 is very efficient. The ISP is going to hand out its ISP prefix right here to each customer. This is what it's going to get. And then it's going to assign these to each customer. Very simple example, but it can easily work this way. And they have a /48, so they give us a /48. We then add our subnets if we need to and make it up to /64, which gives us just a ton of subnets without having to think about subnetting. They just have, these numbers would just be different on each router interface. No big deal. But what happens now is we just send this information to the ISP, and notice how it's routing this information. It's kind of nice, very efficient. And once it gets to it's going to take off the ISP and the global spaces here, and then we're just going to send the 2001 here to go to the IPv6 internet. So we're only going to announce the /32 here, and this will be the /16 network here. So this is relatively very efficient, much more than IP version 4, which gives us very efficient and scalable routing, improved bandwidth, and functionality for user traffic. To assign IPv6 global unicast addresses, remember there's two different types, static and dynamic. In static, we do a manual interface ID, which means we'd go and use either DHCP, we call that stateful, and we DHCP or go to each host and put an IPv6 address on it. That seems like it would be an awful lot of work. What we're going to use is called the EUI64 interface ID assignment. What this does is take the MAC address of the host and add it to what we send it, the /64, and now we have a 128 bit address, and so it's very unique for every host. So this is called auto configuration or stateless. So what we want to do is do EUI64 stateless auto configuration by just configuring our routers with this EUI64. I'll show you this, and there's another larger example in my book in chapter 13. So again, this is the easiest way to do it. Now, I'm not just showing the easiest way that won't work in a large enterprise. This absolutely would work at any large enterprise network the same way, and I actually highly recommend it. Now, the EUI64 interface identifier is basically, here's my MAC address, here's the first 3 bytes, here's the last 3 bytes. It actually inserts an FE in here, and so now we have what? 8 bytes. So it's a modified EUI64 address. So instead of 6 bytes, it's 8 bytes. Now, we can use this for interface identifiers and expands the typical 48-bit MAC address to 64 bits by replacing or inserting FE into the middle, 16 bits. Now, this is to make sure that the chosen address is from a unique Ethernet MAC address. Now, this is going to be set to 1. Now, if you ever studied the 1 and 0 here, universally unique or locally unique here, this is either set to a 0 or 1. 0 would be, hey, it's 0 for local scope. 1 would be it's a global. So we would typically have this set at 1. And it's not something that we have to modify, although we can. Stateless auto configuration, request solicitation request prefix. So we want the /64 from the router. This is going to send the network type information, prefix default route, which is itself. And remember, every router would do this and answer, so it would have multiple ways out. And then send the router advertisement, just keep sending the router advertisements. So the router solicitation, 3, host auto configured address is prefix received plus the link layer address. So to use the link layer address or the EUI64. This is how we probably want to set up our networks. And if you're working at home on this, this is how I would set it up. It's the easiest. DHCP v6 stateful is an updated version of DHCP for IP version 4. Supports new addressing. Server 2003 can do it, and Server 2008. Enables more controlled and stateless auto configuration. Can be used for renumbering, used for automatic domain name registration of hosts using dynamic DNS, and other things. So remember, there's stateful and stateless. Stateful meaning we're going to statically assign them onto an interface, static IPv6 addresses onto an interface. That's a lot of work. We can use DHCP for this, though. Stateless is probably the way to go because there's nothing wrong with auto configuration, but you do lose some control that DHCP will give you. So in some larger corporations, we may want to use stateful. Let's take a look at it. DHCP v6 is an updated version of DHCP for IP version 4. We can run it on server 2003 and certainly 2008. So it supports the new addressing, gives us more control, can be used for renumbering and automatic domain name registration. So one of the good things is helps us use dynamic DNS. So in a larger corporation, this might be something that you need to do. IPv6 routing protocols, we could use all sorts of routing protocols, pretty much everything we used before. Static, RIP, OSPF, even EIGRP, ISIS, and BGP. We don't necessarily need to be worried about most of these routing protocols. We'll just talk about RIP, and this stands for Next Generation. Now, to enable any routing protocol, we must enable IPv6 routing on the router. It is not enabled by default. Remember, if you try to do IPv6 routing and it doesn't work, it's because your iOS does not support IPv6, so make sure that it supports IPv6. So the IPv6 unicast routing command, that's the first thing we turn on a router to basically say, use IPv6. If you type that in and it doesn't work from global config, you need to change your iOS. So now, RIP next generation. Similar to IP version 4, it's distance vector, radius of 15 hops, split horizon, poison reverse, based on RIP version 2, but unlike RIP version 2, doesn't suck as bad. Updated features for IPv6. We use the prefix next hop address. We use the multi-group. Remember, we use 224.0.0.9, so this is the link local FF002::9, so it'd be all zeros 9. And uses IPv6 for transport. So, of course, we're going to come from RIP. And remember, RIP runs at the application layer, unlike the other routing protocols, so it's going to use IPv6 when we get to the network layer. And, of course, it's named RIP Next Generation, RIP NG. Could have been RIP v6, would have been fine with me. Now, one of the things is if we're doing a transition and we have IPv4 traffic here, which we will have, and IPv6 network here, it certainly may be the other way around for this example, but it doesn't make any difference. We have an IPv6 network here, IPv6 here. We need to get from here to here, and we need to go over an IPv4 network. We could do transitioning, tunneling. So there's different ways to do it. Dual stack, manual tunnel, 6-to-4 tunnel, ISOTAP, Teredo. And we can also use something called NAT PT, so we can do NAT, but we don't necessarily want to do that, but we certainly can do this, a type of NAT that allows us to transition across here. Now, to dual stack, Cisco iOS dual stack, basically what this says is that we have a router that runs both IP version 4 and IP version 6. So if I have hosts in here that run IPv4 and IPv6, and I'm sure we'll see this for a really long time to come, that our router needs to run both. So IPv6 only hosts can communicate and get out of the network and then come back and communicate to the IP version 4 hosts. So this is not really a great way to go, but it is a way to work, and it certainly will work. I don't think we have a choice but to run dual stack for a really long time. Typically a host like this that's running IPv6 will run IP version 4 as well. Certainly you can go to all your hosts and send out and tell all the hosts to say we're going to disable IPv6 and now profiles or something like that when they log in that disables IP version 4. We're probably going to see that in the future, but I don't think we're going to see that all in 2008 at least. Now, the dual stack configuration on a router, pretty simple configuration. One thing, as I told you, for the router you have to say IPv6 unicast routing. If I type config T and it doesn't take this command, upgrade your iOS. Maybe it's downgrade your iOS because you want to get IPv6. It depends. Now, on interface E0 here, we have an IPv4 address and an IPv6 address. So we say IP address, which means we're using IP version 4. To type an address on an interface, it's IPv6 address. So we type in the address as short as possible and use a /27. I like to use even shorter addresses, but this is an example of a dual stack router. So to tunnel, if we did have that, we would have our IPv6 network over here. Tunneling is an integration method in which IPv6 packet is encapsulated within another protocol, such as IP version 4. Tunneling is not new. We've done this for many years. So it includes a 20-byte IPv4 header within it. So we're going to have the IPv6. We're going to add the IP header in front of it. Now, so then we have the IP. So basically, we add the IPv4 header on top of the IPv6 packet. And this allows us to route through the IPv4 network. Then we rip off that header and we're stuck with just the IPv6 packet over here. For us to do this, we must be running dual stack routers. So manually configured IPv6 tunnels, we could go through and put it would look like this, IPv4 and IPv6 addresses right here. Notice that we have the same addresses here, different interface. Now, this is configuring where it's : 3, all zeros, 3 here, and : 2 here. These are manually configured where we're not letting them auto-configure. I even let these auto-configure. I just put in the first 64, the first /64, and let it auto-configure the rest. It actually will work, and I'll show you that in the lab. Dual stack endpoints, IP and IPv6 addresses configured at each end, and able to make this work. So to enable IPv6, basic configuration, and this is exactly what I'm going to do, IPv6 unicast routing, and then IPv6 address, the prefix with a /64. And now I'm going to let it, with this EUI-64, we're saying just the 64. We're going to give it the first 64 out of 128 bits, and it's going to go ahead and use the MAC address and make up the rest. So we're going to call that, let it do it on its own or stateless. Now, IPv6 address configuration example. So I'm going to come here, turn on IPv6, and now I'm going to say IPv6 address here, the /64, EUI-64, and here's, let's take a look at what our address came up with. So 2001. Now this is my what? Link local, because it starts with FE80, doesn't it? Now here's my first part of my /64. Now it inserts the rest of the address, my MAC address, doesn't it? To come up with my other 64 bits. So remember, because it was only a 48-bit address, to get it to 64, we insert the FE here. And now we have this other 64, and this is now a